Hello students. So carbon dating technique. So this technique is one of the main technique in order to find the life period of any old object like prehistoric animals, plants, what is the ages of these objects, artifacts we can use based on carbon dating technique. This technique works on the principle of half-life of carbon 14 isotope. You already know every isotope, every radio isotope has its own lifetime, yes or no? Based on the lifetime of this isotope, we can able to find the age period of the prehistoric things like animals, plants, anything. So because the half-life of any nuclide is constant, it's a constant, yes or no students? Like carbon 14, some many years, radon these many days, so uranium some billions years. So this half-life is constant for all the isotopes. It is not changing for atom to another atom, it is constant. So based on this number we can able to find the life period, the age of the fossil. So the amount of substance remaining in an artifact can serve as a nuclear clock to determine the ages of the objects. When an animal is alive, it maintains a carbon 14 to carbon 12 ratio identical to that in the atmosphere. When it dies, this ratio decreases. By measuring this ratio and contrast to it to the atmosphere, we can get an approximate age of that object. Students, we are all made up of carbon, yes or no? In general, living things are made up of what? Carbon only, right? Living things, of course carbon is also present in the non-living things. This carbon is present in how many types? Carbon 12 is there, carbon 13 is there, carbon 14 is there. So when the animal or anything is alive, it maintains that carbon 12 to carbon 14 ratio in respective with the atmosphere. But when it dies, this ratio will start decreasing. Based on the lifetime, when it start decreasing, they can able to find the age of that object. You already know half-life means what? 50% of the amount will get into the disintegration, yes or no, converts into radioactivity, radioactive decay undergone. So based on that life period, based on the nuclear clock of carbon 14, from when it starts, we can estimate the age of that particular object, the prehistoric animals or plants. That technique is called as carbon dating technique. So radioactive disintegration series. Many of the naturally occurring radioactive nuclides have relatively short half-lives. For example, radon 222 isotope, students, which causes between 5,000 to 20,000 deaths per year from lung cancer. This radon 222 is the reason for many deaths. You already know why? Because they emit radioactive substances, yes or no? Alpha rays, beta rays. What happens if they emit? When we expose to that substances, what will happen, students? They create cancer cells to our lungs and tissues. So and this radon has a half-life of only 3.82 days. How much? Very short half-life, yes or no? 3.82 days only. Sir, if 3.82 days only, from billions of years ago this earth is there, so why still radon is there? Like why we are exposing to radon? The reason is, students, this radon is getting reproduced by the radioactivity of another isotopes. Understood? What is happening? This radon is getting reproduced because of the radioactive decay of another higher isotopes. That's why radon is produced and it again converted into another element. Ultimately, what is the cause of radioactivity? From unstable state to the stable state, they undergo based on by the emission of alpha particles, beta particles and gamma rays. So the reason is, with such a short half-life, why are these and other short-lived nuclides are still around? The answer is that although they disappear relatively quickly, once they form, these nuclides are constantly being reappeared because they are the products of other radioactive substances, other radioactive decays. Understood? That's why again they are produced. And short life, in that short life, if we are exposed to that, then what will happen? That creates a danger, health hazard, students, mostly cancer. So and all are short-lived only? No, some of the isotopes, radioactive isotopes, have long lives also, half-lives also. Let's see. For example, uranium 238 with a half-life of around how much, students? See, 4.51 billion years. How much? Uranium 238, 4.51 billion years, which changes to lead 206 is a mass number, students, in a series of 8 alpha decays and 6 beta decays. So it's a long-lived isotope, sir. Ultimately, in these years, what is happening? Half of will get reduced and it converts into another stable form. The other two important decay series are the one which uranium-235 with a half-life of around 7.13 into 10 to the power of 8 years decays in 11 steps to lead-207. So ultimately they are converting into the stable element which is lead with mass number 207 here, 206 there. And the one with thorium with mass number 232 which has a half-life of around 1.39 into 10 to the power of 10 years decays in 10 steps to lead-208. These nuclides undergo a number of alpha and beta decays resulting in the formation of stable isotope of the element lead. These are the three series can be represented. We can see the series of these isotopes nuclear representations. Look at here, uranium 238, 92. You already know these numbers. 92 is the atomic number, 238 is the mass number. It is getting converted into which element, students? Lead. Yes or no? Lead. By releasing 8 alpha decays, and this is beta. What is alpha? Helium nucleus. What is beta? Electrons. Yes or no? And these electrons are getting released from where? From the neutrons. Yes or no? Neutrons undergo breakdown to form proton and electron. These electrons, high energetic electrons, will be released. And this series is called as 4n+2 series. Why this is called as 4n+2? I'll explain. Listen. Next, uranium 235 converts into lead with 7 alpha decays and 4 beta decays. This series is called as 4n+3 series. And finally, thorium 232 thorium converts into lead with 6 alpha decays and 4 beta decays. This is called as 4n series. Why this is called as 4n series? Why? Because look at the mass number of thorium, 238. It's a multiple of 4. Yes or no? It's a multiple of 4 5s are 20, 4 8s are 32. Right? Got the clarity? So that's why this series, the number 4 is a multiple of the mass number of thorium, so called as 4n series. Then why here it is called as 4n+2? Why? Because after by dividing the mass number of uranium with 4, we'll get a remainder of 2. That's why it is called as 4n+2. What is the number 2 indicates? The remainder in this division. So 235 by 4, here the remainder is 3. That's why 4n+3 series. If the remainder is 1 with a multiple of when it is divisible by 4, then that series is called as 4n+1 series. If it is a completely divisible, then 4n series. Understood? Got the clarity, students? So here next we have neptunium series is an artificial radioactive decay series when the mass number of these are divided by 4 and the 1 is obtained as a remainder. So this series is called as 4n+1 series. Understood? What the 4 indicates? The multiple by the mass number, and 1 indicates the remainder when you divide it. So neptunium converts into bismuth with 7 alpha decays and 4 beta decays. Ultimately, students, all these are getting converted into the stable form by releasing radioactivity. What is radioactivity? Either alpha ray, beta ray or gamma ray. So calculation of number of alpha rays and beta particles. Students, we have two formulas to calculate. First of all, number of alpha particles can be calculated based on the difference in mass number of parent and daughter nuclei by 4. Okay, parent and daughter means what, students? Parent means before the decay, daughter means after the decay, the nucleus which forms after the decay. So this is the formula, and to find the number of beta particles emitted equal to this is the formula, 2 into number of alpha particles emitted minus difference in atomic numbers of parent and daughter nuclei. So in these formulas you can observe what is there, students? It's a difference between parent nuclei as well as daughter nuclei. Ultimately we can get this number based on subatomic particles only. Why? Because in this alpha decay or beta decay, which are getting released, students? Protons, neutrons and electrons only. Understood? So these are the formulas you have to remember. So next, applications of radioactivity. Applications means like uses, like where we can observe, where we can see these radioactive elements in the nature and how they are useful. Are they harmful every time? Are they useful? Everything we'll discuss now. Listen, nuclear radioactivity affects many aspects of our lives every day. Radioisotopes are everywhere. They are in the air we breathe, the water we drink, the soil and the building materials we use for our homes. They are also found in the foods we eat to nourish the cells of our bodies. Therefore, we all contain radioactive isotopes. And why we are not harming, students? That it's overexposure to the highly energetic radioactive substances causes damage. Okay, in general in the nature, with the limited supply, it's okay. Everything, the radiation is everywhere. Radiation is everywhere. Then when it is danger, overexposure, direct exposure is danger. Remember? So let's see some of the applications, some of the uses. Radioactivity is used in the nuclear power generation, the future. The future is nuclear power only. Enormous amounts of energy is there present in the nucleus. Sir, students, when Hiroshima, Nagasaki, what happened? Nuclear bomb. How much energy is released? A city get destroyed, right, students? That much of energy is there in the nucleus. So radioactivity is used in the nuclear power generation. That's a, of course, this is present even in the future also. Completely radioactivity, nuclear power. So radioactivity is also used in the radiation therapy, which is the field of medicine, even in the cancer treatment also, to target the cancer cells, to kill the cancer cells. These radioactive elements, these radioactive decays are being used. So next, carbon 14 is used to determine the age of dead plants and animals. This is called as radiocarbon dating technique. We already discussed about this. Sodium 24 is used in controlling the blood circulation and pumping the action of heart. Even in this sodium also, sodium in general 23, this is sodium 24 is radioactive element. So it is also used in the medicinal field. Iodine 131 is used in the detecting goiter. It's a kind of diseases which is related to the thyroid gland, abnormal state of the thyroid gland also. We have this isotope, this radioisotope of iodine is being used. And cobalt 60 is used to control the cancer growth. So most of these radioactivity, radiation is very used, students, mostly whether they're used in the energy purpose or they are used in the medicinal purpose. Yes or no? So that's why if you visit the big hospitals, they have a complete chamber, a block of radiation. Yes or no? Have you seen the skull image? And they'll give you one statement, don't come nearby, a radiation is here. Yes or no? So when you visit any hospital, be careful. Without directly, don't enter into the inside. Why? Because you need to have some kind of clothing to enter into that radiation zone. So mostly in the medicinal field, we use this radioactive element, students. So what are the safety precautions we can get? Of course, whatever it is there in the nature, we don't know, we can't see the radioactive elements. But if you know the radioactive elements are there, what are the safety precautions we can take? The first principle is time. The less time you spend around a radioactive material, the less exposure you will receive. Students, sometimes you have cloths, yes or no? Even some types of cloths with green color coating, which is a radium, green color, which emits glow in the dark, yes or no? That is also radioactive substance. So be careful while using all these painted radium on the cloths, right? So be careful. Why? Because that is also radioactive substance. Overexposure is not good for health. So the second principle states that the greater the distance away from the radioactive source, the lesser your exposure to the radiation. Ultimately, what the safety precaution is, you should avoid being there around the radioactive material. Once or twice is okay. Overexposure is a damage. What damage? Cancer. So lastly, if you can protect yourself with some type of material to act as a shielding device, you will also reduce to overall exposure. So nothing like that, students. Shielding device means in the sense like wearing aprons. How the doctors wear aprons? Yes or no? They have a separate masks and separate whole setup. So with that, you can like slightly, not completely, you can reduce effect of that, but not 100%. Understood? So these are the precaution techniques you have to follow when your exposure to the, if you know the radioactive, this is the radiation zone, don't play with this radioactive element, students. So difference between chemical reactions and nuclear reactions, this also we discussed in the first video. What are chemical reactions? Chemical reactions takes place by the electrons, whether by losing, gaining, sharing. Nuclear reactions takes place by the nucleus. Yes or no? Protons, neutrons only. They are nuclear reactions. In chemical reactions, reactants react and they produce new substance. In nuclear reactions, what happens? This element converts into another element. That's it. So we have many types of chemical reactions, right, students? Many types of chemical reactions like combination, decomposition, displacement, double displacement, oxidation, reduction, reversible, irreversible. Many types are there. So when it comes to the nuclear reactions, mainly we have two significant reactions. That reactions we'll discuss in this coming slides. So the nuclear reaction is a process in which a nuclide is converted into another. Nuclide means you already know a particular species of nucleus with particular number of protons and neutrons. By the bombardment of a particle or a ray, the first nuclear reaction was carried out in the laboratory by the scientist Rutherford by bombarding nitrogen 14 with alpha particle coming from a radioactive source. On the other hand, a chemical reaction is a process in which atoms combine just by the transfer or by the sharing their outermost shell electrons. That is a chemical reaction. So we have two types of nuclear reaction, students. One is called as nuclear fission reaction, other one is called as nuclear fusion reaction. Simple. Nuclear fission means one element converts into different elements. Nuclear fusion means different elements converts into single element. Understood? Fission, fusion. Remember. So nuclear fission, first nuclear fission reactions. The nuclear reaction in which a heavier nuclide, a big nuclide, splits into average mass nuclides of almost equal size with the release of huge amount of energy are called as nuclear fission reaction. That means a big nucleus break down to form two separate equal identical size nucleus. That means ultimately element is changing. Yes or no? If the nucleus, if protons are getting split. So that is nuclear fission reaction, students. So next we have an example also here. Let's see the example uranium. Uranium, how much? It takes billions of years. Then how can we observe, students? For example, honeycomb is there. Honeycomb is, you want to have some honey. You do you wait till all the honeybees till left off? No, right? What you will do? You will hit with a stone. They will get disturbed. Yes or no? Similarly, uranium also, if you want to, that is emitting radiation, it takes this much of time, very long time, long period of time. We can't wait that much of time. Yes, sir. And if you're dropping uranium bomb, are we waiting for billions of years in Hiroshima and Nagasaki? Then how does it happen? Because we are disturbing the nucleus by shooting that nucleus of uranium with subatomic particles, mostly neutron. Neutron is a particle which is not getting deflected by electric field or magnetic field. Straight away it hits the nucleus. Yes, sir. No, simply how you hit a honeycomb with a stone. The simply here also uranium nucleus will be disturbed by shooting the neutron. If that nucleus of uranium with 235 particles, if it is disturbed, just imagine how much of energy is getting released. Enormous amount of energy. The whole city will get destroyed by the shock wave, by the energy wave which is produced. Understood, students? So, and this is what happens. Uranium converts into barium, krypton, and 3 neutrons are released. Here one thing is there. These 3 neutrons again hit the another uranium atoms. And again 3 more neutrons are released from every uranium. It's a complete cycle reaction, students. It's a cyclic reaction. It never stops. If it never stops, that is destruction. Understood? Are we shooting a single atom? No. Got the clarity? It's a chain reaction. So the 3 neutrons released in this reaction bombard with 3 more nuclei of uranium, each releasing 3 more neutrons, and the reaction continues. If this reaction is left uncontrolled, it causes a huge destruction. Simple Hiroshima, Nagasaki, nuclear. And atom bombs works on this process, students, right? So nuclear fusion reaction. Opposite to fission is nuclear fusion. The nuclear reactions in which 2 or more lighter nuclides fuse together to give a stable and heavier nuclide by releasing a large amount of energy are called as nuclear fusion. That means this time smaller nuclide combine to form one bigger nuclide. Understood? That means that type of reactions are called as nuclear fusion combining reactions. So these are the examples, student. Like look at here, how many hydrogens are there? 1H1 means protium. Yes, sir. No, 4 hydrogens are there completely combined to produce 2. Here we have helium as well as we here 2 electrons are getting released. And one is deuterium, other one is also deuterium. They combine to produce a helium and this much of energy is released. Here we have one deuterium and tritium. You already know the mass numbers are different. They are the isotopes of hydrogen. We get a helium as well as 1 neutron is getting released. Hydrogen bomb works on this principle. Whether it is a nuclear fusion reaction or nuclear fission reaction, one thing is common. Enormous amounts of energy. What is that? Enormous, huge amount of energy will be released. Why? Because we are influencing which particles? Subatomic particles, where electrons, no, protons and neutrons, students. That's what. So here, now answer, students. That's it, completed. Now answer, students. What is the reaction happening on the sun atmosphere? What is the reaction happening? Sun atmosphere, sun core, wherever in the sun, what is happening? Is it nuclear fission reaction, nuclear fusion reaction? The answer is nuclear fusion reaction. Hydrogens combining and they're producing helium. In this process, they're releasing enormous amount of energy. that energy is getting emitted as light energy and heat energy. Understood? We are getting heat and light because of that nuclear fusion reaction. So what is the fuel for the sun? Hydrogen. If there is no hydrogen, what will happen? Sun stops burning. That is not burning, of course, let's say energy produced because of this reaction. So that's why even sun has a lifetime, students. After that lifetime, sun will die. It converts into supernova, red giant, neutron star. Some process is there. Got the clarity? So the whole space is completely nuclear factory. The whole space is completely filled with nuclear factory. Why? Because all the nuclear reactions, plasma, energy, dark, everything, all the process happening. Only in our earth, simply all get stabilized, all the elements are there, they are combining to form molecules and they produce cells, tissue, organs. We develop like this, on this condition only. But the major part of the universe is completely nuclear factories. I hope you got the clarities about this chapter. Nuclear chemistry, students, very interesting chapter, and there are very main points also you have to make a note about. I hope you got the clarity. Thank you, students.